Hi, it's Daniel Brown here. Today we are going to talk about interest and compound interest. To start, if one borrows money, then one expects to pay interest, right? If you borrow money, if you would borrow $1,000 today, and if you have to pay it back in a year, you would expect to pay back a little more than $1,000 in a year. If one lends money, so if I lend $1,000 today, then I expect to receive interest. I expect to receive a little more than the money I lent at the beginning. The interest is usually given as a percentage of the principal over some given period. So this is called the interest rate. Now, the interest is computed periodically and is either paid immediately or added to the principal. If the interest is added to the principal, then for every period that passes, interest is accrued on a larger principal amount, and this is known as compound interest. Two key concepts within finance, within all of finance, is the concept of present and future value. If we invest an amount P into an account, the amount of money will grow in the account over time. The value of the account at some point in the future is called the future value. Every different point in the future, so 1 year, 2 years, 3.5 years, whatever it happens to be, will have a different future value. If we know we're going to receive an amount, let's call it A, from an investment in the future, then the value of that account now is called the present value. So again, in 2 years, we're going to receive $10,000. That might be worth $9,400 today. The $10,000 is the future value. The $9,400 is the present value. So the P in our first statement is the present value, and the A in the second statement is the future value. So we have this formula. If an investment earns interest at an annual rate R, compounded M times per year, then the future value of the account, FV, at the end of T years is FV equals PV, the present value, times 1 plus R over M to the power MT. Now, one thing to note, this R is an annual rate, and we divide it by M in order to find the per period rate. Almost always, interest rates are going to be quoted on an annual rate, as an annual rate, with some compounding frequency. So 1 plus R over M to the power MT. The present value, if an investment earns interest in an annual rate R, compounded M times per year, and we know the future value of the account, FV, at the end of T years, then the present value of the account is given by PV equals FV times 1 plus R over M to the power negative MT. And these two equations, the one on the previous slide and this slide, are essentially the same equation where we took the one on the previous slide and divided both sides by 1 plus R over M to the power MT. And that gives us our negative exponent. Now, common compounding frequencies, really 5 that show up regularly. 1, annual. 2, semi-annual. 4, quarterly. 12, monthly. And 365 daily. The last thing we need to talk about is continuously compounded interest rate. If interest is continuously compounded, meaning you earn that interest every instant of time, then a formula has become FV, future value, equals present value, e to the RT, or equivalently, present value equals future value, e to the minus RT. Now, continuously compounded interest rates are really common when doing analysis, and this is because the mathematical properties of E make it nice to work with. On the other hand, almost no one quotes an interest rate as continuously compounded, in part because lots of people don't really know how to use E. And if I quoted an interest rate to someone else continuously compounded, I would also have to explain how to calculate it. And it's easier to explain the previous formulas than it is to explain this one. But very often, if we're doing analysis, there are some properties which make this formula a little bit nicer to work with. Some examples. Let's say we have $10,000 invested in an account paying 4% interest compounded semi-annually. How much will the account have in 3 years? Now notice I haven't said whether that 4% is an annualized rate or a per period rate, and one can almost always assume it's per period. So we have our formula. One can almost always assume it's the annual rate, and we have to divide by m in order to get the per period rate. So FV, future value, equals the present value times 1 plus r over m to the power mt. We're investing $10,000, so that's our present value. So we have FV equals $10,000 times 1 plus 0.04 divided by 2 to the power mt, which is 2 times 3. Put that into our calculator, we get the future value in 3 years is $11,261.62. Our second example. How much should you invest today in an account paying 2% interest compounded quarterly so that you have $20,000 in 4 years? So here, $20,000 represents a future value in 4 years. So we want to find the present value, which is equal to the future value times 1 plus r over m to the power negative mt. Plug in our numbers. Future value is 20,000. The rate is 0.02. M, we're compounding quarterly, so m is 4. And we take it to the power negative 4 times 4. Calculator and out to calculate this out, and we get $18,466 and a penny. Very typically, not always, but very typically, the present value is less than the future value. For the most part, we assume that interest rates are not negative. The reality is that between, say, 2010 and 2018-19, interest rates in much of the developed world were negative. So sometimes it doesn't turn out that the present value is less than the future value. Sometimes that negative interest rate means the relationship's the other way around. Third example. You borrow $20,000 for 3 years and must repay $21,000. What is the continuously compounded interest rate on this borrowing? So we're given the present value, 20,000, the future value, 21,000, and we want to find the interest rate. So we're going to use PV equals FV, e to the minus RT, and we know PV, FV, and T. So 20,000 equals 21,000 e to the minus 3r. We're gathering all the we're putting the e on the right-hand side by itself. So we get 20,000 divided by 21,000 equals e to the minus 3r. Once we've done that, we can use the natural log, and then we know the natural log and e are inverse function. So we take natural log of both sides. Natural log of 20,000 over 21,000 equals negative 3r, where r equals negative 1/3 the natural log of 20,000 over 21,000, where r is 1.6263%. And so this is one of those properties of e, which is nice. Helps us find this rate. Final one, example 4. How long does it take for an investment to double when invested at a semi-annual interest rate of 2.5%? Okay, so if we have a present value, it could be anything. The future value is going to be 2 times that present value. So 2 times the present value, the future value, equals the present value times 1 plus r, 0.025, divided by 2 to the power 2t. We want to find t. So first, isolate the term with the exponent on one side. So 2, we divide both sides by PV, equals 1 plus 0.025 over 2 to the power 2t. We could take the natural log of both sides. Natural log of 2 equals the natural log of 1.0125 to the power 2t. Properties of natural log, we can bring the 2t out in front. 2t times natural log of 1.0125, and then we can solve for t. Natural log of 2 divided by 2 times natural log of 1.0125, or 27.90 years. Okay. Now, one thing we learned, which is true, but one thing we learned which is a little misleading about compound interest, is that the more frequent the compounding, the more money we earn on an investment with a fixed interest rate. Right? If we have a choice between earning 4% compounded semi-annually for 2 years, or 4% compounded monthly, we'd rather choose the monthly than the semi-annual rate, right? We'll earn more if it's compounding monthly. Now this is true, but it's probably not the best way to think about interest. So the interest rate is a convenient way of telling you how fast an investment will grow. If someone tells you that the quarterly compounded interest rate is 3%, they have made a choice of what compounding frequency to use, but they are telling you how fast the investment will grow. If they made a different choice, they would have told you a different rate. So the thing they care about, what they're telling you, is how fast the investment will grow. If they tell you 3% quarterly compounded, they're going to tell you a different rate if they told you semi-annual compounding. And they're going to tell you yet another rate if they wanted monthly compounding. So the reality is the investment is always going to grow at a particular rate. The interest rate is just a convenient way to tell us how fast it's growing, and different compounding frequencies simply mean you're going to have different rates. So this leads to the idea of equivalent interest rates. Given an interest rate R with compounding frequency M, we can always find an equivalent interest rate R bar with a different compounding frequency M bar, such that the future values and present values with these rates will be identical. So for example, here we go. Present value equals this 1 plus R over M to the power MT equals present value times 1 plus R bar over M bar to the power M bar T, where M and M bar are different numbers. So these are both the formula for the future value, and what we're saying is if I'm given a rate R with a particular compounding frequency M, I can find a different rate R bar with a different compounding frequency M bar, which gives me exactly the same answers. So I do some math, present values cancel out, take both sides to the power 1 over M bar T, solve for R bar, and I get this messy formula that gets me between one kind of interest, or one interest rate with a particular compounding frequency, and another interest rate with a particular compounding frequency. For continuously compounded rates, I can do exactly the same thing. Present value times 1 plus R over M to the power MT equals present value e to the R bar T. This time R bar is continuously compounded rate. We do some math, and we can find R bar. So here, if I know my, let's say, semi-annually compounded rate, I can calculate my continuously compounded rate using it. Equally, if I knew the continuously compounded rate, I can do some slightly different math and find the semi-annual compounded rate. So, one more example. What is the equivalent continuously compounded interest rate for an investment earning 4% semi-annually? So R bar from the previous slide equals M times the natural log of 1 plus R over M. Plug it in. Get a semi-annual rate, the rate is 4%, so R bar, the continuously compounded rate, is 2 times the natural log of 1 plus 0.04 divided by 2. R bar is 3.9605. Again, I earn more interest on a continuously compounded basis than a semi-annual basis, so if I'm earning 4% semi-annually, I've got to earn a little bit less continuously compounded for that to be equivalent. One last example. What is the equivalent monthly interest rate for an investment earning 4% continuously compounded? Well, this rate should be a little bit higher because, again, I'm earning interest fastest on a continuously compounded basis. Here, I've just assumed I'm investing $1. So $1 times e to the RT equals 1 plus R bar over M bar to the power M bar T. What do I have to do? I have to solve for R bar. The t's cancel out. E to the 0.04 times 1 plus R bar over 12 to the power 12. Take both sides to the power 1 over 12. E to the 0.04 divided by 12 equals 1 plus R bar over 12. Solve for R bar. 12 times e to the 0.04 divided by 12 minus 1 equals 4.0067. So the interest rate, the equivalent monthly interest rate is 4.0067, and I earn exactly the same amount of money on a monthly compounding basis, at the rate of 4.0067, as I do on a continuously compounded basis with a rate of 4%.